more to a greater width than I actually need. There's the feature that I'm referring to. As long as that doesn't propagate out across the width, it'll machine out because there's an allowance for that in this shop. I'll bring it around here for everybody else. This, this is almost at 90 degrees to the axis of the bar. I've gotten some that were probably a little closer to 90 than this one. Down here is a little bit tighter yet. So you can do that if you're careful. I wouldn't try to go much past this, especially if I was going to flatten that back out. I've definitely noticed that if I'm going to flatten the work, and twisting it real tight like that tends to increase the tendency for it to split on the edges. So we could dry this off and pass this around for everybody. When you're doing thin sections, which I would consider this to be a very thin section, you'll find that to make a thin section thinner requires a lot of power, especially if you're trying to hit specific dimensions like this. The reason for that is because there's not that much open or unconstrained area for the metal to move away from the hammer guide. And so you're trying to basically squeeze more stuff through a smaller area. The smaller it gets, the more power it takes to make that happen. So for that reason, when I'm getting close to being done, I do take my last, when I'm trying to get that thickness, I'll make sure that I'm doing that with the steel at the hottest, or the metal at the hottest point. So that's the first thing I'll do coming hot out of the furnace. Working on the edge, on the lid, there's a lot of space available for the metal to move around at that point, so I don't need to worry about it being quite so hot then. I think you've done it, we're going to get with the hammer. Get that off. We'll let that cool off and then I'll pass that around. How are we doing on time?
4:27.
That's like perfect, right? Supposed to stop at 4:30? Wow. All right, well then I'll turn the forge off. What other questions can I answer for you? Yes. Yeah? Mm-hmm. Of the what? Oh, so the question is, if you're using the like these pressure plates with the bolts to hold everything together in the furnace when you're first putting things together, is there any risk that the plates will stick to the stack of metal? And in this particular case, no, because the way that Mike does this is he wraps that block of copper sheets in a stainless steel foil first. And so it's all encased in a stainless steel shell, and then that's what's compressed. So you have an intermediate layer in there. I think that sometimes there's a little bit of sticking, but by the time I get them, all that stainless has been removed, either peeled off or ground off or whatever. So there is, if you're not using an intermediate layer like that, I think Mike does that largely to keep the metal from being exposed to oxygen, and I think he may even put a little bit of charcoal inside that box as a way to try it and consume any oxygen that might be inside that little stainless steel container that he's created. But if you were going to be making this, like with the C-clamp method that we were discussing earlier, it would be common practice to paint your contact surfaces with some type of an intermediate material to prevent bonding. So in the world of Damascus, a lot of people will use white paint or white out, which has titanium oxide in it, and that provides that. Basically, we could consider it a contaminant. It makes the surface dirty so it won't bond. And there's some other products that the jewelry folks use that are discussed in the books I referenced. So, so yes, it can happen, and because it can happen, you can use that to your advantage if you wanted to bond a ferrous and non-ferrous material. And people have done this for some of, you may have seen in recent years, some guys are making Damascus blades with copper layers in them, and that's exactly what they're doing, is they're just inserting a copper sheet into their stack of things that they're welding together. However, if you do that, you have to be very careful not to get that stack so hot that you melt the copper. Peter knows about this problem. So copper, if you have liquid copper in contact with steel at forging temperatures, the copper can migrate in along the grain boundaries. And copper, if you're forging steel at more normal steel forging temperatures, copper will be liquid. So if you do that, and you then try to forge the steel and you've got contamination from liquid copper, your steel will fall apart, it'll crumble, it'll crack. I've had that experience once at work and a couple times at home where I had maybe done some mocha, got a little too hot, I got a little bit of molten copper in the floor of my furnace, and then came back and forged steel later and picked up some copper in the surface of the steel and forged the steel, and the surfaces were tearing up on me. That's not a common problem to have happen, certainly not in industry. That's an exceptionally rare thing to have happen in industry. I've only ever seen it once in our industrial work. And I tried to figure out how it happened, because it happened in the inside of a big ring. And so we started by taking a solid piece and punching a hole in it and then putting a pin through it and opening it up on a mandible, which I had described a little bit last night. And the problem was primarily in the ID of the ring. And it was tearing up, and the guys were having all kinds of trouble, so they called me and we looked at it. It was sort of beyond salvage by that point, let it cool off. But I looked at the material that it was, the type of steel it was, and said, well, this is not typical behavior for this kind of material. It was like 4140. Yeah, it was 4140. So it's not normal behavior for 4140 to behave that way. It's very easy to forge steel. So after the part was cooled, we cut it up, and I looked at it under the microscope, and I found copper streaks in it. And I had no idea where they came from. The only thing I could think of was that we do forge some bronze components, and we make bronze rings from time to time, and so I thought, well, maybe there's cross-contamination between the tools. So we looked into that. There hadn't been that type of work on those tools for quite a number of months, so it didn't seem like a likely source of contamination. I talked to the steel supplier, they had no idea where it came from, so it's still a mystery. But I will say that under a microscope, that looks really, really cool, and it really does. So I have a 4140 microstructure in the as-forged condition with no heat treatment, which is not how you normally would look at 4140, because typically it's a grade which is going to be subjected to some form of heat treatment. So that would be the time where you would do microscopy. So this is an as-forged microstructure, and it has these bright copper streaks going through it. And there's one particular spot where, if you orient everything correctly under the microscope, you have this sort of peaked copper thing like this. And so I took a picture of that, and now if you ever catch me on like a virtual call, I'll have that, and I'll be positioned so that my head is right under that, and it's kind of like my metallurgy magician's hat.
I heard that's a way to screw up somebody's forge welding by putting a penny.
A penny. So, yeah, I've heard that too. I don't think that the presence of the copper in the forge by itself is the problem, but copper in contact with your metal will definitely cause an issue. And I have actually another show and tell piece that we can pass around. This is not a problem from copper, but copper contamination would look very similar to what you see here. So there's an interesting story there. I had a hammer in at my shop a couple years ago, and some fellas brought some material on that they wanted to have knocked down to smaller size. Pardon me a moment. And so I said, well, what is it? They go, well, we don't know what it is. It came from a family blacksmith shop that's been in the family for years and years. Who knows how old it is? We don't know. I said, okay, well, what size would you like? He said, well, can you make it 3/4 square? We'd like to make some, use it to make some draw knives. We're going to forge weld steel edges to it. Sure, that's no problem. But we didn't know what it was. So, and the bar was, I don't know, 3 feet long. It was a rectangular cross section with a double angle on one side. I have no idea. It looked almost like a press brake die, but I'm sure that's not what it was. I have no idea why that form was created. But I didn't know what it was. They didn't know what it was. And being that it was old, I thought, well, maybe it's wrought iron. If it's wrought iron, I'm going to need to work it at a pretty high temperature so it doesn't crack apart. That's fine. So let's test that. So what I did was, and if you're paying close attention, you'll recognize that I'm bringing in testing into how do we do testing in the blacksmith shop when we don't have a fancy lab like I have at work. So what did I do? I cut a little piece off and I put it in the forge and I intentionally heated it to a relatively low temperature. And then I took a cable and I pounded on it a little bit. Because if it were wrought iron, especially like the puddled wrought iron that we were discussing earlier in the day, forging it at low temperature would probably cause it to crack apart and crumble, and people have all kinds of challenges with that material. So I thought, well, we'll try to rule that out right away. Forge it at low temperature. Actually, the forge was fine at low temperature. So I'm like, okay, that's not wrought iron. Or at least if it's wrought iron, it's really good wrought iron. So I shouldn't have any trouble working it in sort of just normal steel practices. So in the fire pit, pulled it out, and I had, I don't know, 18 inches of it hot or something like that. Went over to the power hammer, had some tooling available to control size, just like we were doing here. Thump, 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 pieces started falling off the bar. Completely falling on the floor. One of them is the one I'm passing around. Cracks everywhere. What is that? This is not supposed to happen. It's not wrought iron. All right, well, is it maybe a super high carbon steel that has should have been, did I get it too hot for the composition, not knowing, we do a spark check on it, doesn't spark like high carbon steel. I don't know if we did this, but we could have taken and forced it a little bit out, heat it up, quench it in water. Does it get hard? No, it doesn't. Oh my God, this is completely mystery material to me. Right? Well, because I have access to a lab at work, I took it into the lab at work and I said, guys, I want to know what this is. So we cut a little bit off and we test it, and it comes back as pure iron. Pure iron is not supposed to behave like that. Right? Like, it doesn't have any slag in it, it's not wrought iron, it's just plain old pure iron. Not like 1018, like pure iron. That's not supposed to happen with pure iron. So what's going on? Well, I'm looking at the chemistry values we got back from the test machine, and I'm seeing that we have some trace elements of various things in there, which is pretty normal. You see lots of different small amounts of things in steel all the time. One of those was a little bit of sulfur. We have like 0.031 sulfur, which is not abnormally high. Modern sulfur contents in steel are usually not more than 0.040, but they can be higher than that if you have a resulfurized steel to make machining easier, which is pretty common. That's not what this was. This was just a sort of average kind of sulfur content. Look at the manganese. Manganese was 0.041. That's really, really low. Most steel today has some manganese in it, and there's an interesting reason why it does, and that's because of sulfur. Steel hates sulfur, in the sense that if you have sulfur in your iron, what will happen is the iron will combine with the sulfur, make something called an iron sulfide. Iron sulfides have a very low melting temperature, sort of like the copper I was describing earlier. So if you had a high sulfur content iron, even with no other alloy elements present, you could expect to have it be described as red short. You may have heard of that term. We don't see it a lot anymore, but a high sulfur steel or high sulfur iron would be described as red short, and people that knew that about iron for a long time. What they figured out was that if you added a little bit of manganese would combine with the sulfur before the sulfur could combine with the iron, and you would make a thing called a manganese sulfide. Manganese sulfides have a very high melting temperature, so you don't have to worry about them melting while you're forging. And that's why almost all steel today has some manganese in it, even if you're dealing with what we would consider a plain carbon steel. So what happened in this particular piece that we had was the manganese content was not high enough to capture all the sulfur that was present. Even though there wasn't a lot, there was still enough to cause a problem. And when I backed the temperature down, when I did my first test at lower temperature, I was below the temperature where the iron sulfide melted, so it forged okay. It was just had a really low working window. And that's not what I expected. And so when I forged it like regular piece of steel, I got that behavior. So that's the only time I have ever personally encountered that problem, because we don't make steel like that today. We put manganese in there to deal with sulfur, and today in modern steelmaking practice, you can get sulfur out if you want to, and so that's rarely a problem. But you start to see in the literature in the very early 1900s where they recognize that problem. They actually recognized the problem earlier than that, but you start to see published values of what the proportion should be for manganese and sulfur in the early 1900s, like around 1910. At that time, they were saying you need about 4 times the amount of manganese as you do have sulfur. Later on, they increased it to 8 times. I think today you're probably even a little bit more than that. So what I have is a piece where the proportions are about 1.1 to 1 instead of 4 to 1 or 8 to 1, right? And so that's why it has that behavior, which was a really neat opportunity for me to sort of validate what is, been known and described in the literature for a really long time. One of the other really interesting things is how people identify that problem. So when you get into the later 1800s, you start to have the ability to do a pretty good chemical analysis of steel through use of a chemistry lab. Not necessarily the same techniques that we use today, but you can use acids to dissolve different things and analyze those products and come up with a pretty good idea of what the composition of steel is. But prior to that, you didn't really have great ways to analyze steel, and you didn't really need to, because it was just iron and carbon, and there wasn't anything else typically present. But people still struggled with hot short steel. This is one of the reasons why someone was sharing, I think Peter was sharing about Samuel Yellen inspecting raw materials that he ordered coming in, making sure that they would survive various forging tests like bending and welding and so forth, because if they were contaminated either with too much slag or with sulfur, they would behave like this, and that would of course be a problem. And so there have been for a long time sort of physical tests, like the ones I did, that others have done, to establish whether or not materials are suitable for the kind of forge work that Samuel Yellen was doing. There's an interesting description in a book from, I believe it's from 1627, written by a Frenchman named Martha Juice. I may not be pronouncing his last name right, but he wrote 3 books about various physical construction trades. So one is ironworking, one is stoneworking, one is woodworking. And he was a guy that was involved in constructing I think a college, a Jesuit college in France. And so back in 1627, he describes smelling sulfur when he encountered hot short steel or hot short iron. And so he was, the 2 things that stand out to me from that little description, one is he was using his sense of smell to understand the material he was working with, and the other is that he was able to relate the presence of sulfurous smells to core forging capabilities with that material. And it wasn't until, many years later that people even recognized sulfur as an independent element. That the idea of having independent elements didn't really come around until the 1700s. So he was really ahead of the times in being able to make that identification. There wasn't anything he could do about it. Like, he couldn't correct the problem. Once the sulfur's in there, you're stuck with it. But you can at least say, oh, if I smell that or I see that behavior, I don't want that metal, or I'm going to have to forge that in a different way or use it for a different application. Any other questions, comments?
So the principle of what makes something hot short, because it must not be contaminants, bombs.
So, in the case of bronze and brass, which Bruce is asking about, you have materials that have a lower melting temperature than steel. So they're hot short in the sense that we just can't work them at as high a temperature as iron-based materials. But that doesn't mean that they're hot short with respect to their defined working range. Make sense? I mean, are you thinking that you've got bronze of the same composition or should be the same composition if they're working in really different ways?
I don't know. When you think of hot short steel, it's soft. I can sort of understand, is it interfering with the glass?
Ah, okay. So in the case of the hot short steel, what you're forming is a new compound that's outlining grain boundaries, and that compound has a lower melting temperature than the underlying material. So iron sulfide coats the grain boundaries. Iron sulfide melts at like 1730, and we want to forge at 23 or 2400 F. And so now you've got liquid at your grain boundaries, even though the underlying steel is still solid. When you hit it, it falls apart.
It's the same idea.
Yeah, the copper in the steel does the same thing. In other materials, I suppose you could have contaminants. I don't know what those would be for the copper family materials. But generally, sulfur in almost all metalworking is generally considered bad.
You got caught on the post.
The only time where we see sulfur used in a positive way, at least in the steel trades, is where you increase the level of sulfur and also increase the level of manganese so that you, in the end, have a lot more manganese sulfides present. And that gives you some benefit to the machine. So, especially years ago when people did a lot of screw machine work instead of the CNC machining we use today, where they have lots of floor tools. So you're engaging a lot of area along the cutting edge to plunge in to create some unique geometry. Having a free machining, what they call free machining steel, was really helpful. They also used to use lead for the same purpose. Some of you may recognize the grade 12L14. That was one of the easiest to machine steels. It's got lead, it also has phosphorus in it. So it's great if you're a machinist, it's horrible for everything else because lead and phosphorus both do bad things for your mechanical properties. But if those aren't important, then you're just making little widgets and you need to machine precise dimensions and you need to make thousands and thousands of them. 12L14 is the steel used for that. We don't see lots of leaded steels anymore because to put lead into steel, the steel has to be molten, and you're trying to put lead into molten steel. Lead melts at, what, 660 Fahrenheit or something, so you have the potential for an awful lot of lead fumes to be released into the atmosphere. And the lead is not dissolved really in the steel, it's actually encapsulated in the steel. So I don't know if that can leach out or not, but lead is definitely a health hazard in a lot of different ways, so it's not used as much as it used to be.
It shows up in bronzes too.
Yes, so lead is often used in bronze or brasses, and what you see now, and where this has become an issue in certain industries, is like the plumbing industry, where you've got a lot of threaded fasteners that are made from, typically made from cast brass, and then they got to go back and machine threads. They had lead either as an intentional addition, or if it was, lead and copper are often found together in ore deposits, and so you might have some lead just as a carryover. But as municipalities have recognized the health hazards of lead, they've begun to restrict the allowable lead contents in those plumbing fittings. And so you end up with materials that take a little bit more time, a little more difficult to machine. Or you have to try to find alternate ways of improving your machining characteristics because they won't let you use lead in those fittings anymore. Interestingly, we still have lots of municipalities where the main pipes are still lead, but there's a push to take those out of service as well. My understanding is that lead pipes were relatively safe, provided your water chemistry wasn't leaching the lead out of the pipes. If you did something that altered the water chemistry and you started to bring lead out of a pipe into the water, now it becomes a health hazard.
And that's what happened out at Flint.
Right, yeah, yeah. Yeah.
The ability of Core-10.
Oh, Core-10? So, for those who are not familiar with Core-10, Core-10 is a steel which is intentionally alloyed with copper to give it some interesting corrosion behaviors. Core-10 and some similar alloys are used where you don't want to paint products. So generally we find them used in municipal structures like some bridges. We've actually forged that, made large rings out of it, and those become bases for power transmission poles. And the advantage is that this material, it will rust, but it gets basically like almost like a flash rust or a surface layer of rust, and then the rusting stops. And you don't have to go to the expense of using a true stainless steel, provided you don't care that the piece looks rusty. So, forging wise, it's not hard to forge. In that particular circumstance, and I think I know where your question is coming from because it has an intentional addition of copper. As long as the copper is actually dissolved inside the iron and not free to be copper chunks at the grain boundaries, it's fine. If your copper content gets too high, then you have more copper than the iron can dissolve. Then you have the problem I described earlier. Right. So we keep the copper low. You know, there are, I think the copper in the Core-10 type materials is around 2%. You take a little bit. But there's definitely a solubility limit that you'll reach with all of the different alloying elements that you can add to iron, and that solubility limit will change depending on what else is in there. But with copper, you know, the 2% is typically a safe number.
So the forging of it doesn't really destroy the corrosion resistance.
Nope, we forge it all the time. Yeah, it's one of those things that is based on composition and not really anything else. And so your many of your stainless steels have the same property, that you forge them and they're stainless. They're you can heat them up, you can cool them down fast, cold. If it's what we would call an austenitic stainless, a 300 series stainless steel, they're stainless, and there's a few things that could maybe reduce their corrosion resistance, and that typically is the presence of too much carbon. If the carbon reacts with the chromium, because chromium is what makes stainless stainless, the carbon reacts with the chromium, reduces the amount of chromium that's sort of free in the system to help with corrosion resistance, then you can get a reduction in corrosion resistance. So you used to see this in welded steel structures like stainless steel. The example was given to me when I was a student was you sometimes used to see stainless steel swimming pool liners. I haven't seen one in a long time, but they used to do that. And so you'd have sheet metal that would be formed and then would be welded on site to, so you had no seams in whatever your pool lining was. And sometimes you would find a situation where you'd have two little lines of rust on either side of that weld beam. The weld beam itself was fine, but on either side of that, you'd have just a little bit of rust. And what had happened was that stainless steel had enough carbon, not a lot, but enough, that when it went through the welding process, there was an opportunity for some of that carbon to react with some of the chrome just in that area, and that localized area was reduced in its corrosion properties. And then when you put chlorinated water in there, chlorine is a pretty corrosive chemical, then you would see the difference in corrosion properties in those areas. So you can avoid that problem by using extra low carbon stainless steel, which if you're interested in that kind of stuff, you would be purchasing something like 304L or 316L. The L at the end of that name means low carbon, so that you don't have that problem. Other questions? Yes? Oh, forge welding the big rig. Just do a YouTube search for forge welding the big rig. Forge welding the big rig. That's the name of the little video clip. Yeah. Yeah. It's a fun video to watch. really good. And if you watch it like 5 or 10 times, and initially watch what the guys are doing who are the subject of the film, and then later on, pay attention to what's happening in the background, because there's a whole other team of guys doing other work. You can't see what they're making, but you can see that they're just working away, completely ignoring the camera and whatever else is going on in the shop. They have their own project and they're completely focused on that. And it's all hand work. You see a guy's head and a sledgehammer just keep flying around. It just looks like a windmill. It's pretty fun to see.
I thought they were the supervisors. I thought they were dressed better.
Well, yeah, in that video you see the supervisor in a bowler hat and a vest. Yes. Good. Other questions? Yeah.
This morning you talked about metal fatigue a little bit.
A little bit, yep.
I always wondered exactly what was going on there, because my understanding of elastic deformation is that the molecular bonds are like stretching and then stringing back together exactly the way they were before, right? So if you compress a spring a million times, it should never change. So what happens when it's fatigued?
Okay, that's a really technical answer, and I don't remember the question from college. But, so what you're describing is what we have, just for background for the rest of the group. Metals can behave like rubber bands. You can stretch them and let them go, and they'll go back to their original dimension. And we know this is true because of the spring example the gentleman just gave. We have a spring, we stretch it, we've increased its length a certain amount, we let it go, and it goes back to its original dimension. Likewise, a leaf spring under a big truck, it bends and it comes backward. So we know that metals can have that property. And all metals have that property to some degree. We usually measure that through a tensile test. I think I described some tensile tests earlier in the weekend, maybe not in a large group, but you can take a piece of metal, make a standardized specimen, put it into grippers, and pull on it in a very controlled way, and you can measure how much it grows versus how much load you're putting on it. And you can also measure when it starts to plastically deform, meaning that when you take that load off, it's going to stay at the new length. But if you take the load off at some lower amount, it'll actually go back to its original dimension, right? So that's the elastic behavior, and then we have plastic behavior. So theoretically, yes, if you always loaded something in the elastic regime, you would think it would last forever. The actual practice, it doesn't. There is a limit where you get what we call fatigue failures, and so you do sometimes see that. Sometimes fatigue failures are happening where maybe there is some plastic deformation happening, maybe not a lot. It's a little bit one way, then a little bit the other way, and like the paperclip is probably my favorite example, because we probably all have gotten bored and taken a paperclip and gone back and forth, and eventually it broke, right? So that's sort of a simple example of that. But I was giving that fatigue example in the case of like the big wheel flanges on the big trucks, right? So there is that back and forth bending, and the part designer, if they're doing a good job, should be designing that part so that it's only ever seeing elastic